Today, we're going to tackle something that sounds like it's straight out of science fiction. We are going to virtually crash test a skyscraper.
So think about this for a second. It's a massive engineering puzzle, right? You've got this plan for a tower that's going to scrape the clouds, but you also need to make sure it can handle the most powerful forces nature can throw at it. And you can't exactly build a test version to see what happens. So how do you know it's going to be safe?
Well, here's the crazy answer. You build it twice. But the first time, you don't use a single piece of steel, not one drop of concrete. The first time, you build it entirely inside a computer.
Okay, let's get into how this actually works. The magic behind all of this is an incredible piece of software called ETABS. Now, that stands for Extended Three-Dimensional Analysis of Building Systems, and it's basically the gold standard for creating what we call a digital twin of a building.
A digital twin. Now, this isn't just some pretty 3D drawing you'd see in a sales brochure. No. You need to think of it more like a perfect virtual clone. Every single beam, every column, all the materials, they have the exact same properties they would in the real world. It has weight, it has strength, and, most importantly, it has potential weaknesses.
So how do engineers get started building this digital skyscraper? Well, it begins pretty much the same way a real building does, with a blueprint. A virtual one, of course.
All right, the first few steps are absolutely foundational. First, you tell the software the building's address, where in the world it's going to be built. This is crucial because it automatically loads all the local engineering codes, in this case something like the IS 456-2000 for India, making sure the design is safe and up to code from day one. Next, you lay out a grid system. Think of this as the building's skeleton, setting the exact location for every single column. And finally, you start stacking the stories, telling the computer exactly how many floors there will be, say 42 of them, and how tall each one needs to be.
Okay, with that blueprint set, it's time for the fun part. We get to tell the computer what this virtual skyscraper is actually made of. We're getting into the real nuts and bolts now. Or, the concrete and steel.
So the engineers define the exact materials. They'll specify something like a high-strength M40 grade concrete. Now, concrete is amazing at resisting being crushed or squeezed, but it's brittle. It'll crack if you try to pull it apart. That's where its partner comes in, steel rebar, like HYSD 500, which has incredible strength when it's being pulled. You put them together and you get reinforced concrete, a wonder material that can handle both squeezing and stretching. It's basically what makes modern skyscrapers possible.
Now that the materials are defined, the building really starts to take shape. Using that grid we made, engineers literally draw in all the parts. They add the massive horizontal beams, place the vertical columns, and lay down the concrete slabs for each floor. And here's a really critical part. They add shear walls. These are these super reinforced concrete walls, usually built around the elevator core, and they act like the building's spine, bracing it against any sideways forces like wind or, you guessed it, earthquakes. And just like that, our digital twin is fully built. It exists right there in the computer, a perfect mirror to its future real-world self. So now comes the moment of truth, the whole reason we did this in the first place, the stress test. It's time to try and break this thing. So in the world of engineering, the forces that a building has to deal with are just called loads. And before we can run our test, we have to tell the software exactly what kind of punishment this building is expected to handle over its lifetime. These loads come in a few main flavors. First, you've got your dead loads. That's the relentless, never-changing weight of the building itself. Then you have the live loads. That's the unpredictable weight of all of us, our furniture, our stuff. And then you have the forces of nature. Wind loads pushing on the building's face. And the big one, seismic loads, the forces that shake a building from its very foundations.
And the analysis begins. First up, ETABS calculates the immense force of gravity, the dead load. We're talking millions of tons of concrete and steel, all pulling the structure straight down.
Then it layers on the live loads. It simulates what a fully occupied building is like. People walking around, furniture on every single floor, adding thousands and thousands of tons of constantly shifting weight. Next, it's time to unleash the wind. The software throws simulated hurricane force scales at the skyscraper, creating this massive pressure on one side and suction on the other, basically trying to bend the whole structure. And finally, the ultimate test. ETABS simulates the violent, chaotic shaking of a major earthquake. It whips the building back and forth, from side to side, stressing every single beam, every column, and every connection to its absolute limit. The virtual ground stops shaking. The simulation is over. So, did it survive? What's the verdict? Well, ETABS is about to tell us. And the answer is a resounding yes. But the software doesn't just spit out a simple pass or fail. It confirms that the design can take all that punishment, and it does so in the most efficient way possible, so no materials are wasted. It's ready for the real world.
And here's where you see the real power of this whole thing. ETABS can tell us exactly how the building is going to behave. For example, it can calculate that during the worst of that simulated earthquake, the very top of the 42nd story, it's going to sway a maximum of 15 inches. Now, that might sound like a lot, but for a skyscraper that tall, that's perfectly and safely within design limits.
So, the final result of this entire virtual ordeal is the master blueprint. And I mean a highly detailed set of plans that tells the construction crew the exact size of every beam, precisely how much steel rebar to put in every column, and exactly how every single joint needs to be connected. It's the instruction manual for a skyscraper that's already proven it can survive the worst.
Think about it. This kind of technology lets us build higher and safer and way more efficiently than ever before. Which really brings up an exciting question. If we can safely test any design we can dream up to its absolute breaking point before a single shovel ever hits the ground, what will the skylines of tomorrow really look like?